So, as a brief introduction, let me just describe the situation with the potential unwanted applications, and or that we can abbreviate to PUA, or also called poor. So, if poor slips my tongue, just remember that's PUA. It stands for potentially unwanted application. Overall, the number of infected, considering the volume of infections and detections that come with the telemetry, the malware consists of, it's relatively a small chunk of the entire scope of detections. So I would say that poor is probably the biggest problem on macOS. If you look at the customer base, our customer base, then malware would probably be intercepted on 1% of that base, while potential unwanted applications go up to 16%. So the chunk, the volume of people affected by poor on Mac OS platform is substantially larger. Looking at the geographical location of where the telemetry is coming in, the mostly affected regions are the United States and Europe, but there is also a fair bit of reports coming from Australia, South Korea, China, some other places. But that also backs up or underlines where our customer base is located. If you look at the top malware threats, there aren't that many, or the biggest problem would probably be sitting in that long tail covered by other. But if you consider the potentially unwanted application share, it's a much more diversified place. You have many more vendors fighting for the crown in that area. So let's get into the analysis of the application. It is distributed as an installer bundled with various forms of potentially unwanted applications. So to give a bit of context, there are many developers that build software and they want to make it free. They want to get some reward for building it. So they come to the service of this company and they bundle it with the pool, and that installer gets distributed. Once the customer clicks it and then the installation goes ahead. And for each installation, this is how the monetization works. So for each installation, the developer would be rewarded. So right now on the screenshot, you see the actual installers of this particular software. Again, the names are blurred because the developers have nothing to do with that. They're probably just, even though they're part of this game, they are fully legit, fully clean installers. So no questions to the actual software that they develop. Okay, so the DMG file comes in, it gets mounted, and we can have a look at the content of the file, of the directory structure. And if you open up the plist, you can see that the key CF bundle executable is responsible to identify the actual binary, the main binary. In this case, it's called advancingly, but there are different names. So it's whenever you pull a sample from Aristotle and have a look at the name of the executable will be random. So it's randomized, but random in terms of it consists of random words. Fatherless, try house and tell me, whatever. Then it doesn't matter. But just remember that it's random. The DMG file itself is not signed, but the main executable is always signed, and the developer ID is always valid. It's a valid developer ID, but as it was mentioned in the previous ADA talk, the developers are cycled, so you can see many developers. You can't specify which one is most prevalent because they always change. But it's always signed, so it bypasses gatekeeper, it runs, and now it's time to analyze it. Right, so how do we analyze it? First thing, let's have a look at the file entropy. Right here you can see that most of the file has a flat entropy, which is the first sign that the file most likely, or most of it consists of some compressed data and or encrypted data, but it falls over, so there is a little drop here that's probably responsible for the digital signature, and there is some area over here which most likely corresponds to the code, to the actual executable code. So you understand that the entropy, like whenever the file is compressed, so the distribution of different bytes it varies. So you can find and counter any bytes of any value, and this is where the entropy is flat. Now remember that, because that will be you'll see later what happens with the compressed data. So let's load it up into either disassembler. And the first thing that you might encounter, the first thing you might see, that the entry point starts from some garbage bytes that make no sense. There is no valid opcode, there is no actual code to execute. So how does it run if there is no code to run at the entry point? Where does execution start from? Does anyone have an idea?
Static initialization.
Hmm?
Static initialization.
Yes, there are. In this particular case, the initialization is delegated to there is a concept of lazy and non-lazy classes. So what is non-lazy class is also called an eager class. That's the class that gets realized when the program starts up. That's the first thing that happens. And these classes, they also have the method called class load, as opposed to these non-lazy classes that are lazy classes. That's the opposite. And these classes that do not have class load method, and these classes don't have to be realized immediately. So they are realized whenever they receive the first message. Now that we know this, there must be non-lazy classes that get with the low class load method implementation, and that method will be called first thing before the entry point. How do we find it in the actual executable? Let's have a look at the actual source code of the Objective-C runtime. The first snippet is in the Objective-C runtime new.mm. In that file, you can see that it's calling a function called get Objective-C to non-lazy class list. That function returns the list of classes into this variable class list, and it also returns the count, how many non-lazy classes are out there. Then it starts the loop, and in that loop, it runs up to the count number of non-lazy classes, and for each class in that class list, it calls realize class function. That function itself, you can have a look at the another source code of C file.mm. It's right here. You can see the macro where it obtains the list of non-lazy classes from the section called __Objc _NL CLS list. So where NL stands for non-lazy, CLS stands for class list. All right, so that's the name of the section. Now let's find that section within the executable file. In IDA, just go to the section, and in the list of all the sections, we can find that particular section right here, and proceed to that section. And over there, you'll see two descriptors of Objective-C classes. The first one is called, in this particular case, called listed UPay3, but it's also a random name. So whenever you pull a different executable, that name will be different. The second Objective-C class is, in this case, it's called arclight. That seems to be constant. Now what we can do, we can proceed and find where the actual code of the class load method of that particular class, what it does. And if we proceed to that method, you will see that there's a valid code for it. No more rubbish bytes or anything like that. There is a valid code, but immediately what strikes is that that code is doing something interesting, something that reminds you, probably if you come from the world of Windows now, it reminds you, really strikes rings the bells, right? So you have, let's have a look. You have C character put in AL register, then AL is put into EBX plus 8. So EBX pointed to the memory area, into the buffer where the string is composed, and RPX plus 8 means starting from the start of the buffer, count 8 bytes and put C in there. So you'll see goes right here, and so on. So let me run it as a little animation. So that's C _, O, termination 0, R, M, and so on. So you can see it randomly composes that name, and once it's fully composed, that name becomes the protect. So what does it do with that name next? Next, it's called VLC function. That function will obtain the pointer into vmprotect function implemented in the dynamic library. It's similar to getProc address in Windows when the APIs called dynamically. By dynamically obtaining the address of that function, then calling that function by the pointer, right? So similar approach. What does it do with the protect syscall? What is it trying to do with that function? How it's called? And here is the context of the call of this function. This function is called with 5 parameters. And you can see first one is own task. Second parameter is, so just by looking at this scheme, it's trying to assign certain flag to a memory chunk. And that memory chunk corresponds to the code section of the executable, __ text. How does it do it? It finds the location. There is an anchor located inside that section. Call it anchor, you can call it marker, it doesn't matter. It's a variable that has specific offset from the start of that section. And it's away from the start of the section by about 3,000 bytes. So what it's doing, it's taking the address of that anchor minus the offset, which gives you the start of the section, followed by 14K, that's the size of the entire code section in the executable, and following with vmprot_all. That's the flag it wants to assign to its own code section. What vmprot_all means, it means a combination of 3 flags: read, write, and execute. So initially it has read and execute flags, but it also assigns it write access. So it wants to get write access into its own code section. Once it does it, what it next step it does, it decrypts that code section with a hard-coded 32-byte XOR key. That's the XOR key, and again it's random key, and every executable it's a different one. And once it's fully decrypted, the code section will have a valid code in it. And after that, the actual entry point within that code section will get control. So it will start executing from the entry point of the executable. The question is, what is that anchor? And if you look at the memory of that anchor, you can see that it consists of encrypted bytes. So once the code section gets decrypted, what does this anchor become? And let's run, in this particular case, I'm using either freeware debugger in the debugging mode, and I was actually using RLDB debugger because it gives the surgical precision to do what you want to do, but for the purpose of this demonstration, it's pretty okay to run at least the strict decryption time. So let's run it. But whilst it's executed, keep an eye on this memory area where the anchor itself is located. What becomes with that anchor? So by the addresses, you can see it's dynamically allocated buffer on the heap, so it allocates it, decrypts the code section into that buffer, and then copies back into the code section. So now it's running. While it's running, EAX gets incremented, so it's the offset into the memory, but look at the anchor. Anchor becomes some text. And that text reads as Maxim Maximovich Isaev. So some people probably know that name. Okay, once again, what happens is we have, after the code section gets fully decrypted, at the start address, you can see a valid code. Now it's valid code. It's a normal executable file. It will proceed from that entry point. Now, the anchor, before it was decrypted, it's gibberish. After it was decrypted, it becomes Maxim Maximovich Isaev, which is a real name of Soviet spy, who worked in the headquarters of SS during the World War II. It's a fake person. It's a lead character, come from the book, written by Julian Simonov. He never existed in reality. But by the book, he worked as a deep undercover agent within SS. He diverted the German nuclear vengeance weapon research program into a fruitless dead end. And, well, it's a hidden marker. Why are they using it? I don't know. But I think I owe you to explain the title of this presentation. Why is it called Never Before Had Stierlitz Been So Close to Failure? And the name was Otto von Stierlitz. That was his name by the book. Think of it as a Soviet James Bond. Okay. So these days, it's a commonly used phrase. It's commonly used to describe a situation when someone, not necessarily a spy, but someone's cover is about to be blown. And it's used in daily life in a situation like this. For example, I don't know if you read the news, but there was a beluga whale caught in Norway, and there was a harness strap which says equipment of St. Petersburg, and all the news agencies were saying, oh, it must be a Russian spy. So people's response is, yeah, sure, never before had Stierlitz been so close to failure. Now, other joke situation, you can find them online when people use this phrase, it's something like this, or even this. So, okay, but jokes aside, let's get back to the analysis. All the strings, all the APIs are encrypted, and let's have a look at this particular case. Here on the bottom, you can find the fully decrypted string. It reads NS application name. In order to decrypt it, it calls this function, and let's have a look how it does it. First, it gets the buffer. It puts into the buffer XML word, which corresponds to a 16-byte integer. After that, it takes the buffer plus the offset 16 and appends 2 more bytes. So in total, we have 18 bytes. Following that, it calls the crypt function, and it's implemented right here, when it takes the character and applies XOR operation with an index. In the first case, it's passed as 0, incremented by some fixed number like 13. After that, it puts the decrypted byte into the first byte of the buffer, then it runs the loop where it decrypts all the remaining characters. So the encrypted string becomes NS application main. By reading this code in this assembly, you can basically build a script to decrypt all the strings, all the encrypted strings in the binary. And you will later see that this particular executable has a module. That module will be loaded in memory dynamically. And by applying this script to the module, as it turns out that there were 1,228 encrypted strings in that module, and they were decoded, dynamically decoded on the fly during runtime by using over 1,000 different functions. So that decrypt function is one out of more than 1,000. In each case, the function was doing one of 3 operations, either simple XOR or simple key subtraction or other incremental XOR key, like here. But in each particular case, there was a different key, different number, different value. But by running the tool, it's possible to decrypt them all to understand what the actual executable is doing. What's the logic? To understand its logic. What is interesting is that the obfuscation was changed from around 9th of April 2019. And now this, imagine this number 13 here, right? So that number was now replaced with a function call. So what do you think this function is doing? And that function simply returns number 6. So you see it's a smoking mirror. And if you look at it, so let's say move AL3. So AL gets 3. SHL AL2. SHL shift 2 bits left. By shifting by 1 bit and multiplied by 2. By shifting by 2 bits multiplied by 4. 3 multiplied by 4 is 12. Next, move 12 into ECX, move 65 into EAX, so EAX will put 0 into EDX. ID of ECX, it will divide EAX, which is 65, by ECX, which is 12. 65 divided by 12, whole number is 5. Multiply CL, so multiply EAX, which holds 5, with CL, which holds 12, you get 60. Move CL 65 and subtract AL from CL. Subtract 60 from 65. The result is 5. Then increment CL by 1. CL gets 6. Put 6 into AX, so return 6. So you can imagine the smoke and mirror, the hustle they do to return 6. But if you look at hex-ray decompiler, you definitely a license for that, but hex-ray decompiler it's also cool, but it just collapses the whole thing into return 6. But again, it's also helpful because by doing that, you can immediately it helps to build a tool that can automatically decrypt all the strings contained inside the binary. Now, what happens next? The code is doing dynamic module loading. The way it's doing that, it locates an encrypted data stub in its own executable, which is around 300 to 400 kilobytes. So do you remember that entropy, flat entropy, that corresponds to this compressed chunk of data? It lifts it from the executable file, and then it decrypts it and calls uncompress API from the loaded libz1 dilute. So it uncompresses it in memory, that chunk of data, which becomes almost 900 kilobyte buffer in memory. Following that, it calls two functions: an as-create-object file image from memory and an ESLint module. So what an ESLint module will do, it will load that uncompressed buffer as a module inside of the address space of the actual executable file. And this is when LLDB is helpful because it can debug this executable up to the point just before the actual NSLint module call happens, and give the command image list. Image list will enlist 222 modules loaded inside the executable. Module number 222, it's some system module. Following that, LLDB shows you that the next instruction will be call QR13, where R13 at that particular point is the register that keeps the pointer into the function NSLink module. So by calling that pointer, it will effectively call link module. After the call, so we're stepping over it, so we execute it, and after that, we give it the same command, image list. And the difference is that this time, there will be extra module loaded on the number 223. So one more. The name of that module will be image, as opposed to other full path module names that you see in the list. That one is hard-coded. That's how this is loaded under the name image. And the address where that image is loaded at is 101A 5 zeros. Is it the only extra module loading memory? No, there are 265 in total. So there are more modules loaded. Why there are more modules than if it was just one? Because of dependencies, because that extra module depends on other modules, and they are loaded dynamically as well. So you end up with 265 modules. Now we can give the commands to LLDB by asking it to read the memory from that address where the module is loaded at. Give me the content of the memory. And LLDB returns you some data which starts from common signature of the 64-bit microbinary. So you see this. If you read it from the right to the left, you'll read it feed face. Only feed face is a marker for 32-bit microbinaries, but feed face with F in the end, it corresponds to 64-bit microbinary. So you can immediately tell by seeing feed face, you can see that the module loaded is indeed a 64-bit microbinary. From that moment, that microbinary can be dumped from memory and analyzed again, loaded into IDA, analyzed statically to understand what that module is doing. So what do we have so far? This is the overall scheme. Once again, to repeat let's revisit the architecture. So the execution starts from the plus load method of the Objective-C class before the entry point. Non-lazy class plus load method. That method will take the encrypted text section with entry point in it, then it will decrypt it. Here it is decrypted. Once it's fully decrypted, the entry point gets the control, and this is where the execution starts from. The execution starts from. Once it starts the execution, it will lift the compressed blob around 300 kilobytes, and it will decrypt it, and it will uncompress it into memory. Once fully uncompressed, that module represents itself an engine. It's a powerful engine that can do many things. That module itself has all its strings and APIs fully encrypted. As I mentioned, 1,248 strings in total. The engine itself doesn't do much. The engine is driven with the high-level code, and that high-level code exists in form of SDK. It's written in JavaScript. Again, it's lifted from the encrypted resource, gets decrypted, and that JavaScript will drive the engine to do things. And if you thought it's all, no, it's not all, because apart from that, what it's doing else is going to the remote server and fetching extra tasks, which are also written in JavaScript, and those tasks will drive the engine to do more things. Apart from these things, there is a trickery, which is very common to malware, Windows malware especially. And let's look at one of these tricks, anti-debugging. So it doesn't want to be debugged, right? So if you load it onto, as the next slide shows, try to run it on the debugger, it will fail. Why is that? Let's have a look. ptrace variable gets a D word, that's 4 bytes, encrypted bytes correspond to this. ptrace plus 4, 2 more bytes, ptrace plus 6, 1 more byte. So we have 7 bytes in total. Following that, add to the XOR. That's the function that will take the notified D and XOR it with 2D incremented by this parameter. In this case, it's just 0. The result gets, puts it back as the first character of the ptrace, just like you saw the VM protect decryption. But similar thing. And repeats the loop for 6 more characters, each time calling the same function. In the end, once it's executed, the ptrace variable will hold the string called ptrace, followed by termination 0. Then it will call DLC. Just like before, obtain the function pointer into ptrace call. And that pointer is copied into fn ptrace variable. Following that, call ptrace and return the result. The ptrace is called with the first parameter being pt deny attach. What that flag means. If the process is being debugged, that call will exit. It will exit with the status of E not sub, which means error not supported, error code 45. Otherwise, if you, let's say you run it and then you try to attach the debugger later on to that executable that's already running, with that flag set, an attempt to debug it and an attempt to attach the debugger will result in segmentation violation exception. So it doesn't want to debug it, right? And in practice, how it looks like, let's say we take LLDB and we say, all right, so run sudo LLDB installer app, right? What happens? It's loaded. Then we give it R, run it. What happens? Process exits, and the status is 45. That's the deny attach status. So it fails. It won't run under the debugger. How do we overcome this problem? Under the debugger, we locate. That's why LLDB is good for this, because this is where IDA it's stripping, to be honest. So, but LLDB gives you full control. So with LLDB, let's put a breakpoint on that location where we're about to call the function that calls ptrace. And here it is. So execution breaks of this call. So this call Q, that address, corresponds to the function that calls ptrace. And then the address of that function is F5. The next instruction has the address of FA. And that would be something else. That's a legitimate continuation of the code. That's a continuous execution. So what we do at this point, we'll give a command RE, register, W, write, PC, where PC stands for the instruction pointer. What do we want to write into instruction pointer? We want to write in the contents of PC, the content of instruction pointer, plus 5. Because this instruction takes 5 bytes. You see F5, the next one F8, so 5 bytes. A minus 1 is 5, 10 minus 5 is 5. So we are patching the content of the instruction pointer by giving it a value bigger than by 5 bytes. And that will effectively, and then we say, okay, show me the contents pointed by the instruction pointer. And as you can see, now it tells you that the next instruction to execute will have the address F8, which is here. And that will be whatever, shared load function. So by doing this, we're simply stepping over, without calling it, we're carefully stepping over the actual coding of ptrace. And then we can continue execution, right? So it won't trip on the debugger. Another interesting feature is VM detection capability. So the engine is able to detect virtual machines by using various methods. Internally, this function is called check possible fraud. And the reason why they're doing it is because, it's a guess, is because they don't want developers to benefit by submitting, let's say they submit an installer to various sandboxes around the world. The sandboxes start running it, and with each execution, the developer gets rewarded, right? So they would call it fraud. They would consider this as stealing the money from the company. So they don't want that installer to be run under the virtual machine, under the sandbox. So they detect the presence of the sandbox, just like VMware threats do, VMware malware. And to detect the presence of the virtual machines, they utilize a few different tricks. The first one, they check the MAC address. If it starts from a particular address that is known to correspond to a particular virtual machine, they will say, okay, now I know I'm running out of VM. For example, 001C42 stands for MAC address that's going for Parallels VM. In total, it can recognize over 35 different virtual machines. And here's just a small snapshot of the virtual machines it recognizes. The names you can see here it's how the software is using it internally. So it comes from the encrypted strings. Other methods, so it takes the MAC and IP addresses for all network interfaces, get host UID, it wants to know the discrete from BSD name, it wants to know the USB name, vendor name. It could be something like containing VMware or VBox or whatever. Display ratio, it reads the mouse position since the last mouse moved into that, just to see if is the mouse actually moving. Because if the installer goes on and the mouse is not moving, there's something dodgy, right? Now, system uptime since last reboot, because once the virtual machine analyzes samples one after another, it will probably restore each time the system from the clean snapshot, and that will reset the time passed since last reboot. So by figuring out that time stands constant, it will figure out that it's run under VM. Full path name of the actual DMG file. Some sandboxes may rename the DMG file into hash, right, or give it some generic name. So by fingerprinting that name, they can identify the presence of the virtual machine, position and size of the app window, mouse position to see if the mouse is actually in use. Because if the mouse is not, have you seen Mac? There's no mouse movements and no mouse present. Purpose. Any sandbox has its own fingerprints, right? So they want to know, they learn what those fingerprints are, and then by detecting those fingerprints, they can detect the common sandboxes. Crash logs. The crash logger sends get requests to a remote script. And as you can see, another interesting technique, the remote script is disguised under a PNG file. And the actual crash log consists of crash, OS, AppKit, version, debug, backtrace, some parameters. That's just a little snapshot of the crash log data it submits. But again, interesting technique. This guy's not a PNG. Why? To bypass the firewalls. Because when you look at the logs and you see a normal GET request to remote PNG file, there is nothing wrong with that, right? But in reality, it's actually reporting the data. Configuration files. There are two types of configuration files. One is dynamically extracted from its own body, and that configuration is encrypted with AES 128 algorithm. To locate the actual encrypted configuration file within its own body, what it's doing, it starts parsing the executable from the back up and up to the start, and for each two adjacent bytes, it calculates the difference between them and checks if that difference corresponds to a 64-bit integer. And if it finds it, then say, okay, I found that where that encrypted configuration file is stored, it lifts it, extracts AES key from it, and decrypts it. And here is the snippet of the decrypted configuration file, which consists of things like product type, product description, download URL. This is where the installer actually tries to fetch the remote installer, the legitimate installer written by the developer, to run it on the machine and on the system. So you see, let's have a look at the actual algorithm. So here is the familiar feed face with F on the end, which corresponds to the 64-bit header of the macro binary, and it has this loop. Inside that loop, it gets byte at an index -2. That's a previous byte. Then it gets the current byte at the reference by the index -1. And from that byte, it subtracts the previous byte. And that becomes the difference. If that difference is a negative number, it adds 256 and checks if that difference corresponds to the signature. And the signature right here, you can see it's a 7 integers, 64-bit integers. And if it corresponds, then it will count. So file will keep the count of how many matches it has from that signature. And once it reaches 7, it goes, okay, found injection. By the way, it's internal code injection. That's how it calculates and locates the location of the encrypted configuration file that I mentioned on the previous slide. And the second configuration file is provided in the form of a JavaScript file. So it's decrypted along with other SDK files. And that file, have a look at two important fields here are report server, remote report server, and remote add URL. Report is where it's beginning the data. And in this is an example where it sends this data to. That's what the data is about. Things like HDD size, is user administrator or not, is VM defined, is it running under VM or not. So all these diagnostics is wrapped into the report. It's encrypted with AES 128 and it's submitted in encrypted form to the remote server. So it's for reporting, it's for beaconing. The second server, add server, this is where it's actually fetching the remote tasks. And the data is encrypted. Once the data comes in, it decrypts the data, and the data will represent itself as JavaScript, and the payload will be wrapped into section name tags. So we'll extract it and execute the task. So the engine will be driven with this remote task. Now it's probably the time to tell you what the engine can do, right? By the way, the analysis of this task will normally use activity in that, but just out of curiosity, to understand full functionality, full scope of functionality of the engine, it's practically a backdoor. The engine can terminate browser process, can set new home page, it can take screenshots. It takes the screenshots of the location of the mouse. It downloads, executes new tasks. It creates authorization for tasks. System info collection, collecting all sorts of system information, cookies from the browsers, lists of installed running applications, checking the personal VM, adding moving applications to from dock. Get info about connecting iOS devices. So the device class ID, serial number, It has full file system capability, so it can search for files. It can save data to files. It can read data, create, delete directories, launch tasks, application as root, display alerts, download files, collect network information, and collecting all the detailed information about the system. So it's practically a backbone. Now, the final questions that come in mind are final conclusions. So first thing, it's a very popular bundle. The website says that it has millions of downloads. I don't know if it's true or not, but this is what they claim. The engine itself, the capability of the engine, it reminds a fully written backbone because I unlocked full access to the system. Memory injection and other techniques, obfuscation techniques, string API, encryption, dynamic API loading, all these techniques, the obfuscation, the very techniques, they just smell like Windows malware. They just remind you, especially if you've done a fair bit of malware analysis for Windows. Then the things like all the tasks are symmetrically encrypted. So the question I have, what happens if the control is intercepted? What happens if someone intercepts the control and feeds rogue tasks into that system? What happens if the developer goes rogue and tries to get unauthorized access to those installers? Having the sheer complexity and the power of the engine, is it really justified? The trend it backs up, it demonstrates is the spill of the traditional Windows malicious techniques. So it's runtime packing, string obfuscation, as I mentioned. And finally, what I wanted to mention is that there was no malicious activity found in the tasks, right? However, and I have no doubt that the company has good intentions by building such a powerful backbone in the engine. And what those intentions might be. Let's say there is a fraud activity, or there is a suspect that some developers are trying to milk the system and game the system, right? And they're trying to get rewards by doing some fraudulent installations or some replication, so they want to put a stop to that. And to stop it, they might need to extract more information, to learn where is it running, is it a new sandbox, what is the context of that fraud. So for that investigation, they may have implemented that engine, but I personally question what happens if someone gets intercepts control. Can you trust those developers that have control to the system? And so I have no doubt that the intentions are good, right? So, but we all know what road is paved with good intentions. So I'll leave it to that, and that's the end of the presentation. Thank you.
Mahalo. Are there any questions?
Thank you. It was a great presentation. I have two questions. Do you know what is the percentage of macOS malware that tries to exit or avoid VMs with these sort of detections?
For Windows, it's a common trend.
Yeah.
It's been. I remember presenting a virus bulletin back in 2007, and the presentation was called "Go and Unleash," and the whole purpose was disturbing trends that we are dealing with malware that doesn't run on the sandboxes. So all sorts of trickery to detect the VM. On Windows, so over time that became. You look at the obfuscators like Finita, Enigma, and other really hard to be tough protectors. They all are capable of detecting the virtual machine. Finita just pops up saying, "I don't run on the virtual machine," right? On the other hand, on Mac, I personally haven't seen, but maybe I'm not that experienced, but I haven't seen anything that has a VM-aware or VM-aware approach. So that was a discovery for me. But again, I want to clarify that this is not malware. Right? But the technique is there.
And thank you. And my other question is, so this level of complexity for software malware is commonly seen in Windows, but maybe not as much on Mac. So is it becoming more common to see this level of complexity for
Well, as you see, I'll mention one thing to you. I did mention it during the presentation. Do you remember I mentioned that in April they have changed the encryption method, the obfuscation method. That happened on the 9th of April. On the 5th of April, Boris Goldin published a program for the forthcoming presentation in October, and they put this title on the website. That was on 5th of April. 4 days later, the encryption was changed, Stierlitz was gone, and more obfuscation was added. I don't know if it's a coincidence or not. I just don't know that. But the complexity is there. You can see it. It's a demonstration. It's there. You can pull these things, and it pretty much reminds Windows. If you wanted to predict what happens next, we can probably expect. Again, it's speculation, but we could probably expect the complexity of the runtime compression and obfuscation seen in Enigma, Armadillo, Femida, and so on and so forth. So, like the Protect. We could expect that on Mac, but again, I'm just speculating. I don't have a crystal ball.
Okay, thank you.